Assalamu alaikum. Dear learners, I hope you are fine. In this video, I am going to give you a tutorial on how to use RSLogix Simulator to simulate some of the ladder logic diagrams which we have already seen in the previous videos. So getting right to the point, if you have seen how to install a PLC simulator video, you must have these three folders in your C drive and in the program files. So to use the RSLogix Simulator, the first thing you should be running is the RSLinx. This software in fact connects the physical hardware PLC with the software of the RSLogix. But right now we don't have the physical hardware. That is why we are going to use an emulator, which I'll talk about in a bit. So the first thing is to run this RSLinx. Open this thing and browse to this application file and double click it to run it. You should be seeing this window. This means that the RSLinx is now running. So now I'm just going to minimize this thing and go back. And now I'm going to run RSLogix Micro, that is the RSLogix software onto which we are going to program the ladder logic. Click on this RS500 icon. This is the window of the RSLogix Micro Starter Lite. The first thing you need to do is you need to create a new project. And for that you can go to the file menu and click on new, or you can click on this new icon over here. Now it will ask you to select the type of the PLC that you have attached. So in this simulator version we can use any of these PLCs. For the time being I'm going to use RSLogix 1100 series A PLC. So click on it and click OK. Now you have selected the PLC and its corresponding modules have been automatically loaded. By default, there are a certain number of I/O modules attached with this PLC. So right now we are going to use those modules only. However, if you want to add more, you can go to this I/O configuration over here, double click on it. Over here you can see the list of modules that are in fact attached with the simulator or is present in this software that you can add. For example, we can add this input module. You can just click on it and then drag it over here. So it has been added. Otherwise, there is an option to read the I/O configuration automatically. This option is used if you are using a physical hardware PLC. Then all the modules that have been attached with the physical hardware, this software will automatically read them off. But right now we haven't added anything, or we haven't attached any physical hardware. That is why we are not going to use this thing. Over here you can see that now we have this module as well. But right now we are not going to use it. So I'm going to delete it once again. I've just did this thing to show you that how you can add more number of modules. So right now we have only 0 module over here, and it is RSLogix 1100 series A PLC. Now let's see that how many input or outputs this PLC has. You can come over here under this data files heading. You can double click on this O0 output and it will open up all the present outputs. So right now if you place your cursor somewhere over here, you can see the address of the last output that is available. That is O:0/63. And the first output that is available is O:0/0. So it means that you have 64 output ports on this PLC, which are quite enough. And one more thing is that you should note the address which has been shown over here. For example, for this output, the address is O:0/26. So if you want to use this output, you should address it as O:0/26. Similarly, for the inputs, you can double click on this I1 input. And now over here you can see all the inputs that are available. So the first input is I:0/0 and the last input is I:0/95. So it means we have a total of 96 input ports available on this PLC. These are all the input and output ports that can be used in the ladder logic program. So now let's get to the ladder logic part and create our first ladder logic program. To create the ladder logic program, the first thing is you need to select the rung into which you want to add the component. So this is the only rung over here. So I'm going to click on it to select it. And now to add the component, there are certain options given over here. As the first example, I am going to implement an AND gate. So for AND gate, I need two normally open switches connected in series with each other. So clicking on this thing will add a switch over here, and it is a normally open switch. But right now there is a question mark over here, which means that this switch has not been assigned any physical address. That is, it is not corresponding to any input port. So we can double click on it and add an address to it. So I'm going to use I colon 0/0, that is the first input address. If you'll press the enter right now, it will ask you to add any description. So I can add, for example, button 1, or you can say it is input A. Click on OK, and now you can see that input A is appearing over here, which is signifying that what is the name of this input, and the address of this input is shown like this. That is I colon 0. 0 stands for module, and this 0, which is written at the bottom, stands for the terminal number. So after that, I need one more normally open switch in series with this one. So I can just click on this normally open button, and it will add the next button in series with it. Once again, following the same routine, I'm going to use the next input, that is I0/1, and then I'll press enter, and I'll name it as input B. So that's it. So now I have added two normally open switches which are in series with each other, and the last thing that I need to do is I need to add an output over here. So I'm going to click on this output symbol, and right now you can see that the output has been added on the right side. So you must remember from the previous video that all the inputs are assembled on the left side, whereas the outputs are assembled on the right side. So it automatically adds the output on the right side. Similarly, I'm going to double click over here and add O colon 0/0 and press enter, and I can name it as output. So very simply, this is the first program, or this is the rung that implements the AND gate. If both of these inputs are high, only then the output would be high. Otherwise, the output would remain low. To save time, I'm going to implement some more logical functions in the same program. For example, if we want to add an OR logical function, then how we can do it. So I'm going to use the next rung to add the OR logical function. So select the next rung, and for OR function, I have to add these two normally open switches in parallel with each other. So I'm going to add the first switch like this, and I'm going to label it as 0:0. I'm labeling this thing same as the above one, so that when I'll actuate the input number 0/0, then it is actuated everywhere. So if it is present in the AND rung, it will be actuated over there, and if it is present in the OR rung, it will be actuated over there as well. So it has automatically labeled it as input A because we have already used that input port. So now I'm going to add a normally open switch or input B in parallel to this thing. To add something in parallel to the other component, the first thing you need is a parallel branch. Parallel branch can be added through this symbol, which says rung branch. So I can click over here and it will add a parallel branch. But right now you can see that this branch is not in parallel with input A. To make this branch in parallel with input A, you have to select this end of the branch and then drag it to the left side and release it over here. Now this branch is in parallel with input A. Now to add something in this branch, you have to select this corner so that whatever input you are going to add, it is added into this branch. Now click on this normally open switch. Now you can see that it has been added in parallel with input A. So double click on it, name it as I colon 0/1. So once again, it has automatically picked up from this part that it is input B because I have used the same input address. So now I'm going to add the output of this OR function. So simply I'm going to use this output button, but make sure that you have selected this end so that the output is added after these two parallel components. So for this thing, I'm going to use another output. So I'm going to label it as O colon 0/1, and I'm going to name it as output OR. So let me name the first output as output AND so that we can know that what is this output, and the second output as output OR. So now the first rung is representing the AND gate and the second rung is representing the OR gate. Now in the same ladder diagram, I'm going to add one last rung that will implement the NOT gate. And for NOT gate, we have to use one input only, but it should be a normally closed input. So I can use this normally closed input over here. You can see that it is already energized. The green line shown over here means the input is energized. So right now there is no green line over here, no green line over here, and none over here. That means that all these input and outputs are not energized right now. But this normally closed switch is energized. So we are going to name this thing as input A, that is I colon 0/0. So it is now input A, which is now represented by a normally closed switch over here. And I'm going to add an output over here. This output would be O colon 0/2, and I'm going to name it as output not. So that's it. Now this is the ladder diagram that we have created. The first rung is implementing the AND gate, the second one OR gate, and the last one NOT gate. Now to proceed, you have to verify that this ladder diagram is correct and doesn't contain any errors. For that, you can come over here, click on this verify file button. At the bottom, you can see that verify has completed, no errors found. It means that our ladder logic program is good to go. One more thing you might have noticed is that there are now module numbers written underneath these input ports as well. Once you have verified the file, the next thing is you have to verify the project, that the overall settings of the program are good. All the settings contained in the processor or IO configuration and all the things which are present on the left side are okay. So click on this verify project. It will verify it, and as there were no errors, we are good to go. Now we have to save this file by clicking on this save button. You can save it with a name, with any name. For example, I'm going to save it with and or not. Now it is saved. Now the thing is we need to run the physical hardware, which we don't have. So we are going to run the emulator instead. Now go back to this folder, C drive folder, and now come to RSLogix Emulate 500. Double click on it and then run this V032. Now this is the RSLogix emulator, and it will run the physical hardware of the PLC by using the ladder diagram which you have just created. It will pick up the configuration, the processors, the power source, and everything that have been embedded in that project which we have just created, and will use that information to run the physical hardware. So now the RS links will think that a physical hardware is running, and RS links will link that physical hardware with the RSLogix 500 software. To use this emulator, click on this open file and browse to the location where you have saved your ladder logic diagram. So this was what we saved, and or not. So double click on it, and now you have to select the station on which this is running. I can select, for example, 1 and click OK. And that's it. So it is running now. Now you just need to go back to RSLogix and come to the communication tab. In the system communication, you can see that now there is another station which is 01. This was the station that we selected. It has MicroLogix 1100 running on it. Click on it, and now you can click the upload button over here to upload the ladder diagram which we have created in this project. It will ask you whether you want to go online or not. Yes, we want to go. Now this rotating icon will mean that we are good to go and our PLC is online. From this drop-down menu, select the run option, and it will change the processor mode to run. Now you can see that these rails are powered up. So now we want to examine that whatever we have programmed is correct or not. The first and the very easy thing is to examine the NOT gate. Right now you can see that there is no input A. Input A is not coming, but there is an output. That is, the output corresponding to NOT gate is energized. So what if I give this PLC a high input A? To do that, I need to right click on this input A, or you can right click on any input A present over here, or over here. So I'm going to right click over here and click on toggle bit. As soon as I click on toggle bit, the input A has gone high. You can see that there is a green line over here as well. And now as this was the normally closed switch, now there is no green line over here. It means that when input A goes high, this thing will go off. So now we can see that when input A is high, NOT gate is giving you a low output. On the other side, if we examine the OR gate, then we can see that input A is high, input B is low, and the output is high. But for AND gate, if both inputs are high, only then output would be high. So right now the output AND is not high. How we can check that thing? I can right click on this input B and toggle it as well. Now you can see that input B is also high, so output AND is high. Over here you can see that for OR gate, both inputs are high and the output is also high. Now what if I close this input A? So I'm going to turn this, or I'm going to toggle this bit once again back to 0 position. As soon as I toggled it, you can see that for the OR gate, the output is still high because input B is high. But the AND gate has gone off because both inputs are not on. And for OR gate, as input A goes low, the output goes high. There's one additional thing that you can see from these files over here. If you double click on this output option, over here you can see that we have used these three outputs. That is the first three outputs, O0:0, O0:1, O0:2. So these registers or these data files are showing that what is the current status of the output. So in this data file, you can see that O:0/2 is high, which is the output not, and O0:0/1 is also high, which is the output OR, and the O0/0 is low, which is the output of AND gate. Similarly, you can go to the inputs and check that what inputs are high and which are low. So we have used only two inputs, that is input A was I0/0 and input B was I0/1. So this is input A, this is input B. Right now input B is high and input A is low. So we have implemented a very simple ladder diagram using two inputs and three different outputs, and we have seen that it is correctly following the AND, OR, and NOT logical operations. Now to stop this thing, go to this menu and click on Go Offline. Now we are offline. Now you can modify this program to anything else, and then you can upload this program once again onto the same PLC and you can run it. Or you can save this program, open a new file, and then upload that new file onto a new PLC and then check it once again. So as an example, I'm going to refer to the last video's example, which we saw over there. This was the example that we saw over there. We wanted a normally open start switch to start the motor and wanted another switch to stop it. When the motor is on, we want a light to turn on as well, and if the motor is off, we want some other light to turn on. So this was the ladder diagram that we made out. Now I'm going to implement this ladder diagram on the PLC and see that whether it is fulfilling our requirements or not. So keep this ladder diagram in your mind. I'm going to modify this ladder diagram. So I'm going to delete these things. By selecting the rung and clicking on delete, you can delete the whole rung. So I have deleted everything over here. Now the first thing is I want a start button. So here is my start button. I'm going to label it as input:0/ for example. Now I'm going to use the input number 10. Enter and then edit description as start. So now this is our start button. Now I want a stop switch in series with this start button, but that stop switch has to be a normally closed switch. So I'm going to add a normally closed switch, name it as or address it as I:0/ for example 11, and in the description I'm going to write stop. So this is my stop button. And for the latching purpose, if you remember that I have to latch this output so that whenever I press start button, and even if the start button goes off, the output shouldn't turn off. So to add the latching option, I'm going to add in parallel a normally open switch that will have the same address as the output. So let me first add the output over here. I can name it as O colon 0 slash, for example, 5, and in the description I'm going to write motor. Okay, now I'm going to add a normally open switch in parallel with the start button. For that I'm going to select this switch, click on the parallel branch. I have added a parallel branch. Now click on this side and drag it over here. Now this rung is in parallel with this start switch. I'm going to select this rung and click on this normally open switch, and now I have added a parallel switch to this start button. I'm going to label it as, or I'm going to address it as O colon 0 slash 5, which is the address of the output. So it has automatically named it as motor because this switch has the same address as this output. So this is the first rung that we have created. Now for the second rung, we need a normally closed switch. It will have the same address as that of the motor, so that when the motor is off, this switch will be on and the connected light on this switch should also remain on. So on this rung, we have this switch, and once again, I'm going to have an output. This output is going to represent the LED or the light that will remain on as long as the motor is off. I'm going to address it as 0 colon, for example, 6, and name it as light off. So this light off will remain on as long as the motor is off. In the last rung, I'm going to once again add a normally open switch, address it as that of the motor, that is O colon 0 slash 5. And for the output of this rung, I'm going to use another output, which is O colon 0 slash, for example, 7, and I'm going to name it as light on. So this light will remain on as long as the motor remain on. So I guess we have implemented the shown ladder logic. Now we just need to verify this project. So it has no errors. I'm going to verify the project as well. So once again, it has no errors. So as the emulator is already running in the background, I don't need to do anything else. I can just upload this ladder diagram into the attached PLC. For that, you should come over here, click on this drop down button, then click on download. Just click on yes, yes, and okay. And now the PLC is running and the program has been downloaded. Now to examine this ladder diagram, click on, once again, drop down this menu and click on the run mode so that the processor can be changed into run mode. Now you can see once again that these rungs are powered up and our PLC is running. So what we wanted was when we press the start button, the motor should turn on. And as long as the motor is off, a certain light should turn on. So you can see that this light off is right now on because right now the motor is off. So I'm going to press this start button, and by pressing I mean I am going to toggle this bit and it will turn on. So I have pressed this start button, the motor has turned on, the light which is the light off has gone off because the motor is now on, and as the motor is on, the other light, which is the light on, should turn on. So right now you can see that this light is on. Now to check the latching function, if I turn off this start button, the motor should not turn off. So I'm going to right click on it, toggle this bit, and you can see that the motor is still on because it is getting power through this rung and then over here and then going to the motor. So right now the motor is on, light off is still off, light on is still on. So to turn off the motor, I need to activate this stop button. So I'm going to activate the stop button by clicking on the toggle bit. And now you can see that motor has turned off, the off light has gone on, and the light on is off. Now if I release this stop button, that is, I'm going to once again depress it or release it, the motor will not turn on. It will only turn on when now I am going to press this start button. So once again, you can see that now the motor is on once again. So dear learners, I hope you have understood the basics that how we can use this RSLogix simulator and along with the RSLogix software to implement ladder logic diagrams and then check them whether they are working fine or not. Moreover, you should understand that what are these registers? These two registers are for output and input. So these two registers contain all the informations of the output. Right now you can see over here that we have used this 5 number output as motor output, 6 number output as light off, and 7 number output as light on. So right now you can see that what are the values of these outputs over here. And for the inputs, you can double click on it, and if you remember, we used input number 10 for the start, input number 11 for the stop. So we have used two inputs, and you can see that right now the start is high because we have pressed the start button, and right now stop button is not pressed. That is why it is off, or it is 0. So I guess this is everything for this video, and I would recommend the viewers and the learners to implement some more ladder logic diagrams using these simulator programs and test your knowledge so whether you can program the PLC using ladder diagrams or not. So this is everything for this video. Thank you and take care.